Hello and welcome to this second session on chemical equilibria, where we will be discussing how to solve chemical equilibrium problems using the knowledge that we have gained about the equilibrium constant and the reaction quotient in the first session. And we'll also be talking a little bit about how changes in the reaction vessel can affect the equilibrium. And this is directly related with the second part of this session, which will be related to Le Chatelier's principle. But first, we will discuss some problems, how to solve them, and look at in detail the processes involved. We look at some reaction tables, which will be fundamental to the future studies where we look at acids and bases, especially with how they are related to weak acids and weak bases. So first of all, I want to introduce this idea that we briefly talked about in the first session, wherein Kc and Kp could be directly related with each other. So K for a reaction may be expressed through using partial pressures of gaseous reactants instead of molarity. So this is in Kc means concentration, Kp means partial pressures. So partial pressures are for gases. You may come across this in other classes. Here, we're going to use them pretty much the same as concentrations. So the partial pressure of gases is directly proportional to their molarity. You probably pick up on that whenever we start to talk about gases in chemistry. So here is a reaction where we have nitrogen monoxide reacting with oxygen to give nitrogen dioxide. So this was one of the processes by which photochemical smog can form. So Qp is equal to the partial pressure squared of NO2. So this squared, remember, comes from the stoichiometric coefficient here. So we're doing this really in a very similar way to the QC. So you can see the QP and QC are very similar, except instead of we work with concentrations in QC, but in QP we use partial pressures. Then Kp can be related directly to Kc based on this Henry's law. So Kc is times the RT to the power of the change in the number of moles of gas. So Kp is equal to Kc times R, which is the universal gas constant, times T, which is the temperature in Kelvin, to the power of delta N, where N is the change in the number of moles. And so if the amount moles of gas does not change in the reaction, then the number of moles of gas is equal to 0. And Kp is equal to Kc. So let's have a look at an example of how to do this, converting between Kc and Kp. So a chemical engineer injects limestone, which is calcium carbonate, into hot flue gas of a coal-burning power plant to form lime, which is calcium oxide. This scrubs SO2 from the gas and forms gypsum, calcium sulfate, hydrated calcium sulfate. So we find Kc for the following reaction if CO2 pressure is in atmospheres. So our balanced equation here is calcium carbonate reacts to give calcium oxide plus CO2. Kp for this is here. So we're asked to convert between Kp and Kc. So Kp and Kc are interrelated like so. So Kp is equal to Kc times RT to the power of delta N, whereas Kc is equal to Kp RT to the minus delta N. So delta N is equal to 1 minus 0, since there is 1 mole in the gas product and none in the reactant. So delta N is going to be equal to 1. So Kc is going to be equal to this times the R value, which is a constant, which would be given to you in any tables, where 1000 degrees Celsius is the temperature we're given Kp at. So that's what we got to work with, to the power of minus 1. Because remember here, and then so that means that our Kc value for this is going to be 2.6 times 10 to the minus 6. And so that's how we would find Kc in an instance where we're given Kp. And now, determining the reaction direction. So we've learned about QC, we've learned about Kc, we've learned that they can be compared to each other, but how do we know what to do with that information? Well, we're going to find out. So determining the reaction direction. So the value of Q indicates the direction in which a reaction must proceed to reach equilibrium. So if Q is going to be less than K, reactants decrease and products increase. This means that the reaction proceeds towards the products, reactants goes to products until equilibrium is reached. If Q happens to be larger than K, then the reactants increase and the products decrease. And the reaction proceeds towards the reactants. So reactants are formed and products are consumed until the equilibrium is reached. And if Q is equal to K, the system is at equilibrium and no net change takes place. This is kind of related with the concept that we learned about in the first session, where we saw that you could start from any position and get to the equilibrium regardless of your starting concentrations. So for example, we started off with some systems that were only product molecules, and actually we formed some of the reactant. So the reaction, direction, and relative sizes of Q and K. So when Q is equal to K, we are at equilibrium. But if Q is going to be less than K, we have a system where the reactants are going to be consumed to form products so that we can move towards a reaction at equilibrium. And if Q is greater than K, then what happens is the products are consumed to give us reactants. So the reaction progresses to form equilibrium, regardless of what position we start at. So using concentrations to determine reaction direction. So for the reaction here, where we have nitrogen tetroxide, dinitrogen tetroxide, then this is in equilibrium with nitrogen dioxide. Kc is equal to 0.21 at 100 degrees Celsius. At a point during the reaction, the concentration of our dinitrogen tetroxide is equal to 0.12 molar, and our nitrogen dioxide is equal to 0.55 molar. And we're asked, is the reaction at equilibrium? And if not, in which direction is it progressing? So we form our reaction quotient based on our balanced equation. In this case, our equation is actually balanced. We have the same number of atoms on both sides. And so we are pretty happy with the setup that we have. Now, QC is going to be equal to the square of the concentration of the products over the reactants concentration. And then that's going to be equal to 0.55 squared over 0.12. So those just came from the question, and we get a value for QC of 2.5. Then since QC is greater than KC, the reaction is not going to be at equilibrium, because to be at equilibrium, QC must equal KC. And this will proceed then from right to left, from products to reactants, because we have, in this case, an excess of products. And so in order to reach equilibrium, we must consume some of the products and return them to being reactants. So solving equilibrium problems, if equilibrium quantities are given, we simply substitute these into the expression for Kc to calculate its value. And if only some equilibrium quantities are given, we use a reaction table to calculate them and find Kc. So reaction tables are really useful. We've seen some uses of those, and we will see a lot of use for those in the future whenever we deal with acids and bases. In acid-base chemistry, especially for weak acids and bases, reaction tables are very important. And so what is a reaction table? Well, it shows the balanced equation at the top. It tells us the initial quantities of the reactants and products, and then it considers the changes in these quantities during the reaction. And then finally, it gives us the equilibrium quantities. So a reaction table example, let's go through this. So in a study of carbon oxidation, an evacuated vessel containing a small amount of powdered graphite is heated to 1080 degrees Kelvin. Gaseous CO2 is added to a pressure of 0.458 atmospheres and carbon monoxide forms. At equilibrium, the total pressure is 0.757 atmospheres. Calculate Kp. So we're actually doing two things here. We're now working with Kp for the first time, and we are going to be looking at reaction tables. Now, don't get too worried. Kp is used in exactly the same way as Kc. So we have our balanced equation there. CO2 plus graphite gives us 2CO. So here is our reaction table. We have pressure. Here we have initial change in equilibrium, which we need. We have our balanced equation along the top. Then we have our equilibrium values here. We have the initial values. So we have initially 0.458 atmospheres of carbon dioxide, and we have no carbon monoxide. Graphite is just there in excess, so its concentration doesn't really change. Then our change here is going to be indicated as minus X for CO2, because CO2 will be consumed to form the carbon monoxide. And the carbon monoxide is plus 2X, because for every mole of carbon dioxide which is consumed, so every minus X, there are going to be 2 moles of carbon monoxide formed. So it's going to be plus 2X. So the concentration or the pressure of carbon monoxide is going. So once we have the equilibrium amounts expressed in terms of X, we use the other information given in the problem to solve for X. So the total pressure at equilibrium is going to be equal to this value that was given in the table, which is 0.757 atmospheres. And that's going to be equal to the partial pressure of CO2 plus the partial pressure of carbon monoxide. So 0.75 atmospheres is going to be equal to 0.458 minus X plus 2X, which is all from the reaction table. If we go back and look, we'll see here at equilibrium, this is the partial pressure of CO2. It's 0.458 minus X. So it's initial minus whatever is consumed. And then carbon monoxide is 2X. So we then fill this in. So we have plus 2X minus 2X. So we end up with this. So we rearrange where X is equal to 0.757 minus 0.458, which is equal to 0.299 atmospheres for X. So then at equilibrium, the partial pressure of CO2 is going to be equal to 0.458 minus X. X is this value. Fill that in, we get 0.159 atmospheres. Now the partial pressure of carbon monoxide is equal to 2X, so it's going to be 2 times 0.299, which is equal to 0.598 atmospheres. And so to find Kp, then we fill that into our Kp expression. So Kp is equal to the partial pressure squared of carbon monoxide over the partial pressure of CO2, which is equal to 0.598 squared over 0.159, which is equal to 2.25. So then calculating Kc from concentration data. So in order to study hydrogen halide decomposition, a researcher fills an evacuated 2-liter flask with 0.2 moles of HI gas and allows the reaction to proceed at 453 degrees Celsius. Two HI molecules then react to give 1 hydrogen and 1 iodine molecule. At equilibrium, the concentration of HI is equal to 0.078 molar. Calculate Kc. So the solution here is to find out the concentration of HI. We know the number of moles, we know the volume of the flask, so we can find out the concentration. So it's 0.2 divided by 2 gives us 0.1 molar. Fill that into our reaction table where we have concentration, a balanced equation, and then the concentrations down the side, initial change in equilibrium. The change will be minus 2X because for every single mole of hydrogen and iodine produced, we must consume 2 HI molecules. So it's minus 2X and then plus X on both sides. So the equilibrium concentrations will be these. Then HI concentration is going to be equal to 0.078, which is equal to 0.100 minus 2X. So that means that X must be equal to 0.011 molar. So then we can fill that into our QC, which is based on our balanced equation. So it's the concentration of H2 times the concentration of I2 over the concentration of HI squared. So it's like this, 0.011 times 0.011 over 0.078 squared is equal to 0.020, which is equal to Kc. So determining equilibrium concentrations from Kc. In a study of the conversion of methane to other fuels, a chemical engineer mixes gaseous methane and water in a 0.32 liter flask at 1200 degrees Kelvin, where Kc is equal to 0.26 for this process at 1200 degrees Kelvin. At equilibrium, the flask contains 0.26 moles of carbon monoxide, 0.091 moles of hydrogen, and 0.041 moles of methane. And we're asked, what is the concentration of water at equilibrium? So this is going to be methane plus water gives us carbon monoxide plus 3 hydrogen molecules. So the solution here then is methane plus water, the balanced equation is this. Here is the concentration at equilibrium of methane. So it's going to be equal to 0.041 moles over 0.32 liters. So we've given the number of moles, we have the volume of the flask, we find moles per liter as so. Do the same thing for carbon monoxide and hydrogen at equilibrium. Then a QC can be found like so. Since QC is equal to Kc, then we rearrange in terms of the water concentration, because that's what we want to know. And then we have an equation like this. We fill in the values from either what we've calculated here or from the table. And then we find out that the concentration is 0.53 molar. Okay, so next, how do we solve equilibrium problems? So solving equilibrium problems, as we've seen, involve a number of steps. So first of all, we have to write up our balanced equation. So this is in our preliminary setup. So then we write the expression for the reaction quotient Q, and we convert all amounts into the correct units, either moles per liter, molar, M, or atmospheres. Then when we work with the reaction table, we need this when the reaction direction is not known so that we can compare Q with K, and we construct a reaction table. Check the sign of X, the change in concentration or pressure. So make sure that we are consuming our reactants and producing our products, or vice versa, depending on the direction of the reaction. So solving for X and equilibrium quantities. So substitute the quantities into the Q expression. To simplify the math, assume that X is negligible. Then the concentration of our species initially minus X is going to be equal to our concentration at equilibrium. And if we have a very small amount consumed, then our equilibrium and our initial concentrations are going to be the same. Then we solve for X, where we check the assumption is justified. So we have about a 5% error. And if not, then we need to solve the quadratic equation for X. And then we find the equilibrium quantities and we check to see that calculated values give the known value for K. So oftentimes in these equilibrium problems, we'll find that the equilibrium lies heavily on the reactant side. And so usually we have to do something industrially to kind of overcome that. But generally, whenever we're just dealing with these equations, it's not such a big concern. There are ways that we will see later with disturbing equilibria that we can solve this problem. So that's why this part 7, where the change in X is negligible, comes in. And so it helps us to solve this problem easier. So here's another question. So determining equilibrium concentrations from initial concentrations and Kc. Fuel engineers use the extent of the change from carbon monoxide and water to carbon dioxide and hydrogen to regulate the proportions of synthetic fuel mixtures. If 0.250 moles of carbon monoxide and 0.250 moles of H2O gases are placed in a 125 milliliter flask at 900 Kelvin, what is the composition of the equilibrium mixture? At this temperature, Kc is equal to 1.56. So here is how we would do it. So we would create our balanced equation at the top. Carbon monoxide plus water gives carbon dioxide plus hydrogen. So calculating our initial concentrations, carbon monoxide concentration is equal to hydrogen or water concentration, which is equal to 0.250 moles over 0.125 liters, which is the volume of the flask, which gives us a concentration of 2.00 moles per liter. Then we create our reaction table, which has got our balanced equation at the top, our concentration changes on the side, and then in here we have our concentrations. Initial concentrations, 2 moles per liter for carbon monoxide and water, 0 for carbon dioxide and hydrogen, because they have not yet been consumed. Then the changes are going to be minus X for both of our reactants and plus X for both of our products, because they're a 1,1,1,1 stoichiometric coefficient. Our equilibrium concentrations are then given as so. And so our QC is equal to KC, which is equal to this expression here, which is the products over the reactants. And so that's going to be equal to our equilibrium concentrations given as X's. So for the products, and 2 minus X for each of the reactants. And so this gives us our new quadratic expression here, where we can solve for our values by taking the square root of both sides. So this is the QC value or KC value that we were given in the question. And then we can find our X value, which is 1.11 molar, by rearranging this. And then we can find out our equilibrium concentrations of our reactants, which happen to be 0.89 molar because it's 2 minus X. Our concentrations of our reactants are just X, which is 1.11 molar. Next problem then, predicting a reaction direction and calculating equilibrium concentrations. The research and development unit of a chemical company is studying the reaction of methane and hydrogen disulfide, or dihydrogen sulfide, 2 components of natural gas. Methane plus H2S give CS2, carbon disulfide plus 4 hydrogen molecules. In one experiment, 1.00 moles of methane, 1.00 moles of carbon disulfide, 2 moles of H2S, and 2 moles of H2 are mixed in a 250 milliliter vessel at 960 degrees Celsius. At this temperature, Kc is equal to 0.036. And so we're asked two things. In which direction will the reaction proceed to reach equilibrium? And B, if the concentration of methane is equal to 5.56 moles per liter at equilibrium, what are the equilibrium concentrations of the other species? So for part A, we'll be calculating the initial concentrations where the concentration of methane is equal to 1.00 moles over 0.250 liters, which gives us the number of moles as being 4.00 moles. Then for H2S, it's going to be 8 moles. For CS2, it's going to be 4 moles. And for hydrogen, it's going to be 8 moles. So that's all just from the question and doing a similar procedure as we did for methane. So QC is then going to be equal to products over reactants. So we fill in the values that we have for the different concentrations and we get a QC value of 64. Now, since QC is much larger than KC, the reaction will proceed to the left. And so the reactant concentrations decrease and the product concentrations will increase until equilibrium is established. So we use this information to construct our reaction table. So the concentration here is given. So this is our reaction table. So we've got the initial concentrations, we have the changes in concentrations, and we have the equilibrium concentrations in terms of X. And so we're told at equilibrium, the methane concentration is 5.56 moles. So our X value must be 1.56 because our equilibrium value is 4 plus X, and that's equal to 5.56. So X must be equal to 1.56. So that means that we can just use that value for X, fill it in, and we can get the concentration for the other things, the H2S, the CS2, and the H2. We're just doing some very simple algebra here. All right. Now we're on to the meat and bones. We've gone through our reaction tables now. We've seen how those work. Let's now consider how we can, in fact, disturb equilibrium. These processes of disturbing equilibria are going to be very useful in sort of overcoming some of the difficulties that we have with industrial reactions. So it's all kind of based on Le Chatelier's principle. So this is the idea that when a chemical system at equilibrium is disturbed, it reattains equilibrium by undergoing a net reaction that reduces the effect of the disturbance. Basically, it reacts to the disturbance in order to try and get back to an equilibrium. So a system is disturbed when a change in conditions forces it temporarily out of equilibrium. So a common one with gases is just to change the volume of the system. And so the system responds to a disturbance by a shift in the equilibrium position. A shift to the left is a net reaction from product to reactant, and a shift to the right is a net reaction from reactant to product. The effect of a change in concentration. So say we have this reaction, A gives B and vice versa. If the concentration of A increases, the system reacts to consume some of it. And so if a reactant is added, the equilibrium position shifts to the right. If product is added, so the concentration of the product increases, the equilibrium shifts to the left. And so that means it's trying to consume B to produce A to try and reestablish that previous equilibrium, which had them at some previous value of concentrations. If the concentration of B decreases, the system reacts to consume some of it. If a reactant is removed, the equilibrium shifts to the left. So if we remove some reactants, the system wants to produce more so that the ratio between the two concentrations is returned to the equilibrium ratio, the Kc value basically. If a product is removed, the equilibrium shifts to the right. So if we remove B, then more A will be consumed to produce B. And so hopefully you can now see why this is useful, because later on, we're going to have industrial processes that are equilibria. And in order to get more product formed, the best way to get more product formed is simply to remove the product that we already have. And so only substances that appear in the expression for Q can have an effect. So previously we learned about heterogeneous systems where solids don't have an effect. A change in concentration has no effect on the value of K. So here we have an equilibrium between PCl3 and chlorine. So the equilibrium lies like this. So PCl3 plus chlorine gives PCl5. So if we increase these, then this will decrease. And then any of these changes causes a shift to the right. So if the concentration of PCl3 is increased, then we get more PCl5. If we increase the concentration of Cl2, then we get more production of PCl5. So if we increase both of them, we get more PCl5. If we remove PCl5, we get a shift to the right. If we decrease the concentration of either of these or increase the concentration of the product, we get a shift to the left. So the effect of added Cl2 on the PCl3, Cl2, PCl5 system. So here we have a system which has started off with a certain equilibrium concentration, and then we have disturbed it by adding something or taking something away. And then we have gone through a new equilibration process to find a new equilibrium with different concentrations of the different species. However, the ratio between their concentrations will be the same as the original equilibrium. So we have this original equilibrium here, then we add a certain amount of chlorine, and then we get a new initial from which we must consume some of our reactants in order to make our product. So that becomes the previous concentrations, the new initial concentrations minus X, which is the change. And then for the product, we have 0.600 plus X, which actually this equals 0.637, which would probably have been given to us in the question. In any case, it is going to be an experimentally determined value in this case. So the effect of added Cl2 on the PCl3, Cl2, PCl5 system. So here's the balanced equation. So we have here the old equilibrium here in this gray box. We have the concentrations here of each of the species, and we have Q equal to K because that's how it goes at equilibrium. Now, if we suddenly increase the concentration of Cl2, we now have disturbed the equilibrium. And so what must happen is that we must consume some of our reactants in order to reattain that equilibrium. So in this white area, there is no longer equilibrium. Q is no longer equal to K. And so the amount of product must increase in order for us to reattain that equilibrium. So when Cl2, the blue curve, is added, its concentration increases instantly. That's the vertical part of the blue curve. You can see it go up here. And then falls gradually as it reacts with PCl3 to form more PCl5. And this equilibrium is reestablished at new concentrations, but with same value of K. So the ratio between the concentrations is the same as before. The K value is the same. The ratio between the concentration of the products and the concentration of the reactants is going to be the same. So Q is going to be equal to K at this new equilibrium. So predicting the effect of a change in concentration on the equilibrium position. So to improve air quality and obtain a useful product, chemists often remove sulfur from coal and natural gas by treating the contaminant hydrogen sulfide with O2. H2S reacts with oxygen to give sulfur plus water. And so what we want to know here is what happens if A, B, C, or D happen. You could pause the video now, try to have a go at it yourself, see what you can come up with. I encourage you to try that, and then I'll go through it with you. Okay, so for part A, we're asked, what happens to the concentration of water if oxygen is added? So oxygen is here. So if we increase the concentration of the products on this side, what will end up happening is that the equilibrium will move to consume them. So it will produce more products. So we will get more water. So the concentration of water will actually increase. Now, part B, what happens to the concentration of oxygen if H2S is removed? So we're decreasing the concentration here. So the equilibrium will move to produce more on this side. So removing of this, so these will be consumed to produce more of this, which means the concentration of this will increase, because in order to produce this from these reactants, we must also produce this. So the concentration would increase. Now, if the concentration of H2S, if O2 is added, so H2S here, if we add more O2, then we're disturbing the equilibrium on this side. So we must move to the right, which means that this will be consumed. So the concentration of H2S will actually decrease because we only added O2. We did not add both. Then what happens to the concentration of H2S if sulfur is added? So if we add more sulfur here, so we increase the concentration of sulfur, then the equilibrium has been disturbed. And so the equilibrium will move to consume this excess sulfur. And so it will produce more H2S. So the concentration of H2S will increase. Coincidentally, the concentration of O2 will also increase. So effect of a change in pressure, the volume of a system. So changes in pressure affect equilibrium systems containing gaseous components. So changing the concentration of a gaseous component causes the equilibrium to shift accordingly. And adding an inert gas has no effect on the equilibrium position as long as the volume does not change. This is because all concentrations and partial pressures remain unchanged. So the inert gas is not actually doing anything. And changing the volume of the reaction vessel will cause equilibrium to shift if the number of gas molecules, if the change in the number of moles of gas molecules is not zero. Changes in pressure, volume have no effect on the value of K. So yeah, so K is still K so long as the temperature remains the same. And changing the volume of the reaction vessel will cause equilibrium to shift if the change in the number of moles of gas is not equal to zero. Why is that? Well, if we think about the way the gases work, they tend to take up space based on how many actual particles there are, how many molecules of gas there are. So if in the reaction, the number of gas molecules on the reactant side is 2, and the number of gas molecules on the product side is 2, that means there's no net change in the number of moles of gas, which means that regardless of which side of the equilibrium we're on, there's going to be no effect of the change in volume and therefore the change in pressure. More pressure will not. So normally, like what you want to do is, as we'll see, is whenever we increase the pressure of a system, the system moves to produce fewer molecules of gas. But if both sides have the same number of molecules, then there's no benefit to doing a reaction, basically. So the effect of change in pressure schematically then, so here we have some reaction vessel, which has a plunger, which can be moved up and down, which will change the pressure inside. So the gas phase reaction then is yellow plus blue gives us a green, and it is at equilibrium. So at higher pressure, so this is lower volumes, so we've pushed the plunger down, we have decreased the space available for the gas molecules. The equilibrium shifts to form fewer moles of gas. So this is where the delta N is not equal to 0. So there are 2 moles on this side, there's 1 on this side. So by consuming 2 moles and producing 1, we reduce the number of molecules in the same space by half. And so what happens is we consume the reactants to form products at higher P. But then if we reduce the pressure, so we pull the plunger up, we increase the volume. And so in order to fill this extra space, to try and approach equilibrium again, the equilibrium shifts to produce more moles of gas. And so the green sphere or circle has been consumed to produce the yellow and blue. The effects of a change in temperature. So to determine the effect of a change in temperature at equilibrium, heat is considered a component of the system. So it's not added to either side, depending on which side produces it. So heat is a product of an exothermic reaction. So the heat of reaction is going to be less than 0. Now, you'll come across these in other general chemistry lectures. We won't deal so much about what exothermic and endothermic reactions are here, except in the sense of how it affects our equilibrium. So heat is a reactant in an endothermic reaction where delta H reaction is greater than 0. And an increase in temperature adds heat, which favors the endothermic reaction. A decrease in temperature removes heat, which favors the exothermic reaction. So again, heat is the product in an exothermic reaction, where delta H reaction is going to be less than 0. So it's going to be negative. And heat is a reactant in an endothermic reaction. So heat of reaction is going to be greater than 0. That means it's going to be positive. And so an increase in temperature will add heat, which will favor the endothermic reaction, which will consume it. And a decrease in temperature removes heat, which favors the exothermic reaction, which will produce heat. So the only factor that affects the value of K for a given equilibrium system is the temperature. So for a reaction where delta H reaction is going to be greater than 0, this is then an endothermic reaction. An increase in temperature will cause K to increase. And so for a reaction which is exothermic, i.e. delta H reaction is less than 0, an increase in temperature will cause K to decrease. So the Van 't Hoff equation shows this relationship where the log of K2 over K1, where K1 is the equilibrium, whereas the previous K value and K2 is the new one at the new temperature, then that's going to be equal to minus a delta H reaction. So that's going to be the heat of reaction over R, which is the universal gas constant, times this 1 over T2, which is the new temperature, minus 1 over T1, which is the old temperature, where R is this value here, and K1 is the equilibrium constant at T1. So how do catalysts affect the equilibrium? Well, actually, they don't do very much. They don't change the position of the equilibrium. They just help it reach the equilibrium faster. So a catalyst is something which provides an alternative reaction pathway to get from reactants to products. So it usually kind of typically speeds up reactions. So a catalyst speeds up a reaction by lowering its activation energy. The rate of the forward and reverse reactions are changed equally. So really, we just reach the equilibrium faster. And the catalyst has no effect on the equilibrium position. It doesn't promote more products. It doesn't promote more reactants. It just sort of speeds the whole process up a bit. So then disturbing the equilibrium via concentration. So say we have this equilibrium where we have reactants on the left-hand side, products on the right-hand side. So if we shift to products, if we increase the concentration of the reactants, so if we have excess reactants, then the system will move to consume those reactants and form products. And then if we decrease the amount of products, then the system will move to consume more reactants to form those products. And so that's, how we could do this industrially. Then if we shift to reactants, if we decrease the concentration of reactants, so if we remove reactants, then more products will be consumed to make them. And then if we increase the product concentration, then more of those products will be consumed to form reactants. And so note that this has no effect on the value of K. It just disturbs the equilibrium. K is still going to be the same. K only changes when temperature is involved. Okay, disturbing the equilibrium pressure. So A plus 2B gives us AB2. So these are all gases. There are 3 molecules on the right or left and 1 molecule on the right. So a shift to products, if we increase pressure and reduce volume, so we produce fewer moles of gas. And we shift to reactants if we decrease the pressure, and this increases the volume. So there are more moles of gas. So we want to produce more moles of gas to fill that space so that we have the same K value, basically. And so on adding an inert gas while maintaining volume will have no effect on equilibrium because it doesn't really do anything in the reaction. And so note that this has no effect on K. So disturbing the equilibrium temperature, this does have an effect on K. This is the only thing which changes K, temperature. So we shift to products if we decrease the temperature, and delta H reaction is going to be less than 0. And this is an exothermic reaction. So we shift to reactants if we increase the temperature and delta H reaction is greater than or less than 0. That's exothermic. So this means that if the temperature is increased, then usually that favors an endothermic reaction. If the temperature is decreased, then that favors an exothermic reaction because the exothermic reaction releases heat, which helps to return the system back to the original temperature or the original equilibrium. And so when delta H reaction is going to be less than 0, i.e. it's exothermic, K increases when there's a decrease in temperature, and K decreases when there is an increase in temperature. Okay, so here is a summary table of all of this. So if we have a disturbance, an effect on equilibrium position, an effect on the value of K, so you'll see most of them have no effect except for temperature. So concentration, if we increase the concentration of reactant, we'll move towards the products. We decrease the concentration of reactant, we'll move towards the reactants. Increases in product moves towards the reactants. Decrease in product moves towards the products. None of these have an effect on K. Pressure, if we increase the pressure, i.e. we decrease the volume, then we move towards fewer moles of gas. So there's no effect on K. If we decrease P, i.e. we increase the volume, we move towards more moles of gas, so that's none. And if we increase P, i.e. we add inert gas, there's no change in volume. So the concentrations remain unchanged and we have no change on K. And then temperature, as I said, increased T, it moves towards the absorption of heat, and decreased T, it moves towards the release of heat. So it moves towards the exothermic side, which will release heat. And then if there's an increase in temperature, the system wants to consume that added heat energy from the increase in temperature and absorb that. And that will cause it to, how do you say this? It will cause it to move towards the endothermic side. Catalyst doesn't really do anything. It just speeds up the process by which we reach the equilibrium. So we reach the equilibrium faster. And so there's no effect on K. Okay, so I talked about this before. We're getting towards the end now of equilibria. It's a relatively short topic, but it's very important, and it will be really important in any study of acids and bases that you do. So synthesis of ammonia. Ammonia is synthesized industrially by what's called the Haber-Bosch process. So nitrogen plus hydrogen gives ammonia. So delta H, the heat of reaction, is going to be exothermic for this process. Now, there are three ways to maximize the yield of ammonia. One is to decrease the concentration of ammonia. So we remove ammonia as it forms. And so that reduces this concentration. So more reactants are consumed to form the product. We could also decrease the volume. That would increase the pressure. So we have 4 molecules or 4 moles on the reactant side, 2 on the product side. So a smaller volume, higher pressure favors the reactants. And we could decrease the temperature, because the lower the temperature, the more energy that can be released by the exothermic process. The problem there is that the lower the temperature, the slower the molecules move, the less chance they have enough energy to actually react. So there's like, what we're going to have to find a compromise, basically. So the effect of temperature on Kc for ammonia synthesis. So if we do it at low temperature, like minus 80, we have 200 degrees Kelvin. We have a very, very, very high Kc value. But if we do it at high temperatures, we have a low Kc value. That's because this reaction releases heat. So an increase in temperature causes the equilibrium to shift towards the reactants, since the reaction is exothermic. But at those low temperatures, which are good for Kc, we have a terrible yield. So look at this. So 200 degrees Celsius, we just have really, really bad, or we have good yields of, ammonia. But the problem is that it takes too long. So at very high pressure and low temperature, the top left, we have a high yield, but the rate is too slow. So it takes too long to produce the ammonia. So we have a sweet spot here, like a kind of compromise between all of these different temperature, pressure, yield here, which is around about 40% yield, which is around about 400 degrees Celsius, about 200 atmospheres or 300 atmospheres. And that produces a very nice amount of ammonia. So here's the schematic of what it looks like. Here's the very first ammonia reactor at BASF in Oppau, Germany. It's just this big long tube here. So you pass the gas from one end through to the other end, and like comes your ammonia, plus the other things actually. So this is the process. You don't need to remember this or anything. It's just for your reference. So we have nitrogen plus hydrogen comes in. We have a reactor here where there's a catalyst. Usually it's iron on a wire. And so the nitrogen and hydrogen are encouraged to react in the reactor at their 200 atmospheres, 400 degrees Celsius, with the presence of an iron catalyst. So after the gas is passed through the reactor, what's happening is that we now have a mixture of the nitrogen, hydrogen, which are unreacted, and the ammonia, our product. So then we pass this through a condensing column. So there is a coolant which passes through this blue, and the ammonia will condense on this condenser, but the nitrogen and hydrogen will not. They have a much lower boiling point than the ammonia. So the ammonia condenses and falls to the bottom where it's topped off and removed. And then we pass the remaining flue gases back in and mix them with the starting materials here, so that we end up producing more and more ammonia. And so when we pass it through the reactor, there should be there shouldn't really be any ammonia. There might be a very, very small trace amount, but that's okay. But by and large, most of the ammonia condenses here and is topped off. So this is held at what, about 400 degrees Celsius, this much, much lower. So in summary then, we have talked about the chemical equilibrium, the equilibrium constant and reaction quotient. We have talked about determining an equilibrium constant. We have looked at using equilibrium constants in calculations. We've learned more about balanced equations and equilibrium constants. We've looked at reaction tables. We've looked at how those can be used. We have looked to find other concentrations, to find Kc values. And we've looked at disturbing a chemical equation. And we've even looked at an industrial example, which shows you the power of chemical equilibria and why it's important to learn about these. Let's check comprehension. So as usual, I'll read out the question, give you 5 or 10 seconds. Please pause if you need more time. You probably will. Just pause, do it yourself, and then we'll go through it together. So for the reaction of dinitrogen pentaoxide, it forms nitrogen dioxide and oxygen in equilibrium. So Kc is equal to 0.21 for this at 100 degrees Celsius. At a point during the reaction, the concentration of dinitrogen pentaoxide is equal to 0.12 molar. That of nitrogen dioxide is equal to 0.55 molar, and that of oxygen is equal to 0.25 molar. And we're asked, is the reaction at equilibrium? And if not, in which direction is it progressing? So here are the answers. So balance the equation first. So we have here an unbalanced equation. So we have to balance our equation. And this is the balanced equation. Then we did this back in session 1. So check out session 1 if you want to know how to balance this equation. Then QC is going to be equal to products over reactants, where we have each of the concentrations to their stoichiometric coefficient. Then we have to fill in the concentrations, which were given at some point during the reaction. And we're given, and we find a QC value of 1.59. This QC value is much higher than the Kc that we're given. So QC is greater than Kc. So that means the reaction is not at equilibrium and will proceed from right to left from products to reactants. So we will consume some of these and we will produce more dinitrogen pentaoxide. Thank you for watching this session on equilibrium chemistry.